You are audible. Yes, sir. Please go ahead.
Okay, sir. Okay, sir. I'll make it full screen.
लाइव कर दिया ना लाइव एंड स्टार्ट
Just a second. Yeah. So, hello everyone. Good afternoon. So, in this session, I'll be talking on colorectal cancer diagnosis using gastrointestinal endoscopy. Right. So, we'll be only focusing on one type of cancer, especially here. That is colorectal cancer, which is one of the kind of GI cancer or gastrointestinal cancer, and the most common one as well, right? So we'll see in details what exactly this colorectal cancer is and how it is currently being detected, what is the gold standard procedure for detection of this cancer, and why we're interested in designing the automated approaches, what is the motivation behind it, and is there any product available in the market or not, what is the current challenges, right, which still persist in the field of colorectal cancer, right? So after discussing all these concepts and all, I'll be showing you some demonstrations, as I mentioned earlier, that I'll show you some demonstrations on attention mechanisms and segmentation approaches. Fine. Let us start. What do you mean by colorectal cancer and how it is currently being detected? Fine. So as we all know, right, from our school level science book and all, that how the digestive system works and what are the components we have in the digestive system and what are the different types of cancer that is possible, right, or that may occur in the GI tract. You can see there are different types of cancer, including the esophageal cancer, gastric cancer, colon cancer, small intestine cancers. Yes, there are small intestine and large intestine, as we all know. There is something called as a colorectal cancer, and there is something called as anal cancer, right? So there are different types of cancer that may occur in the GI tract. Out of all these type of cancers, right, colorectal cancer is the most common one, or you can say, out of all the GI cancers, colorectal cancer holds the rank one, right? Even colorectal cancer is also ranked as the third most common type of frequently caused cancer among all different types of cancers, right? Possible. So for different types of GI cancers, we have different types of approaches to detect those cancers. Like for colorectal cancer, which is the focus of our today's session, and it is detected using colonoscopy. So what is the most important thing we can note down, that if we can detect, right, the colorectal cancer at an early stage, we can prevent this disease, right? You can see also the 5-year survival rate, which is really high, that is 90%. Right. So how how it is being treated? So it is just identify the lesions, or you can say the abnormality regions, and which is basically polyps. I will discuss in detail, right? What is, what kind of what is exactly polyp and how it develops into colorectal cancer over the years, right? And the early stage treatment is the surgical resection. So for surgical resection and for surgical removal of that particular cancer, right? Or you can say the surgical removal of the polyps. So we need actually the accurate or the precise boundaries of the polyps, right? And sometimes even to detect the polyp is very, very different through the naked eye, right? We'll see one by one. So as our focus on in this particular session is on colorectal cancer. So we'll see what is this colonoscopy and what is this process and why there are high miss rates, right, in identifying polyps, is basically develops, or you can over the time, right, you can say, which basically leads to the colorectal cancers, right, over the time. There are also other types of cancers which we have discussed, like esophageal cancer, gastric cancer, small intestine cancer. We have seen in anal cancers, and here is the Here are the detection methods, as well as the early stage treatment procedures and the 5-year survival rate percentages and all. Coming to the statistics of colorectal cancer, as I mentioned, that colorectal cancer ranks third among all different types of cancers, and it also ranks first among all types of GI cancers. Now, let us look at the number of cases that have been reported, right, in the year 2020. So in the year 2020, if you look at the top 10 countries, right, especially, I mean, top 10 means with the highest incident cases, right? In 2020, here there are two different types of bar you will get. One is red bar and one is this a purple color bar. So red color bar is the number of cases that has been reported in the year 2020, and the purple one is the estimated one, right, by 2040. So these many number of cases may arise, right, you can say, from this colorectal cancer. And here are the details, so you can see the statistics of the top 10 countries. So if you see here, the China is having the most number of cases reported in 2020. So US is holding the rank, right? In US also the number of cases are more. In Japan also the number of cases are more. So in our country, right, like India, we had also 30,161 cases in 2020, and the number of cases, right, which is expected, right, you can say in 2040 is nothing but even 64,000. Right? And if you look at the number of cases in China and US, it is comparatively high. I mean, when you compare with our country, that's India. So it is very, very important, right, for us to detect because this kind of cancer is preventable, and if it is detected in early stage and if it can be removed, right, precisely, then we can prevent this kind of disease. And that motivates everyone, right, to design something called as an automated approach. Also, we'll see there are some issues or there are some challenging, you can say there are some challenges, right, that lies while detecting this colorectal cancer. As I already mentioned, that colorectal cancer is the third most common types of cancers among all cancer types, and it ranks first among the all GI cancers, which we discussed earlier. So then how actually this colorectal cancer is being diagnosed, and especially I already mentioned what do you mean by polyp. So polyp is nothing but a small clump of cells, or you can say small growth in the inner walls of the colon. And if it is, if these polyps are actually developed into this colorectal cancer, if it is left undetected, so that means that there's a possibility that some of the polyps, because polyps can have diverse shape, diverse size, and even the colors are sometimes different, and the colors are also sometimes, even the texture of the polyps are very similar to the surrounding tissues. I'll show you with some examples, right, how the colonoscopy images looks like, and where is the challenge and what type of challenge, right, we face, especially the doctors are facing to detect the polyps, right? So there could be also multiple number of polyps. We'll see all these scenarios, right, just the two slides, right? But what is very important for us is this one, right? So early detection and the removal of the polyp or the resection of the polyp can prevent CRC, and that is why we are interested in accurately, or you can say, providing the boundaries, especially to the doctors and all, so that it can be easily removed, right? I'll show you some cases of where even it is difficult for the human eye to detect the polyps, right? And the polyps are actually such growths which always lead to you can say colorectal cancer if it is not detected appropriately. So there are also a few things which is very, very, I mean, which also causes, or you can say create some of the concerns. That is what is, there is no symptom in the early stage, and there's a high risk over the age of 50, right? And colonoscopy, as I already mentioned, is the gold standard for the CRC examination. That is the colorectal cancer examination. We'll see the colonoscopy process right now, right? I'm not going into the details of the whole colonoscopy process and all. So there is something called as upper GI endoscopy, right? Where a tube is placed on a mouth and all. But this colonoscopy is such a process where the doctors place a thin tube, right, in the patient colon. Here it exactly. And yes, it's a difficult procedure, right? That contains a camera. This particular tube, right, at the top, it contains actually the camera and the instrument to detect as well as to remove the polyps, right? So that is what actually this kind of colonoscope, right, camera is trying to do here, and this kind of output actually which you will get from here. But what is the issue with this manual interpretation process, right? So during manual interpretation, the miss rate is in between 6 to 27%, right, which is a really high number, right? So the miss rate, the polyp miss rate is 6 to 27%. And why actually the miss rate is high in this case is because of the huge variations in shape, size, and the color of the polyps. It's only because of the camouflage properties of the polyps, right? So, I mean, I'll show you, right, different types of polyps, right? So these are like the polyps, right? In this case, these are like the polyps, but it is in the colonoscopy image, so it will look like something very different. And I'll show you after just one slide that why it is challenging, and there are different types of polyps available. Sometimes it is flat polyp, sometimes it is sessile polyp and all. So which is always difficult to detect, right, through the human eye and all. So also there is no clear boundary. Sometimes you will also see this case, right? So polyps are having indistinct boundaries. That means there is no clear boundaries of polyps with the surrounding tissues. And boundaries are very, very important for the resection of the polyps, right? So that is what we want actually here. Just can we provide a precise boundary of the polyps to the doctors so that it can be resected carefully, right? Always the miss polyps, right? Always the miss polyps leads to colorectal cancer. So the miss rate has to be reduced, right? So this has to be reduced to even below 5%, even you can say like this, and that is what is possible with the help of this cutting edge AI technologies like deep learning algorithms and all. We'll see. Here are some of the challenges, as I already mentioned, that of course there are a lot of challenges, right, the doctors used to face while detecting the polyps, which leads to the colorectal cancer. And the polyps are having high miss rate, which we already discussed. And the polyps are having large variations in size, shape, and color, right? So there are different types of polyps. You can see over there. Here is a flat polyp, which is very, very difficult to identify because it has the same texture, right, with the surrounding tissues. So difficult to sometimes identify the polyps in these cases, right? Even sometimes there could be lot of polyps, and not all the growths are polyps, right? That also we need to see that not all the growths are polyps. So there must be a huge difference between the polyp as well as the non-polyp regions, right? We'll see whether the existing methods could able to address this kind of issues or not. So in this case, if you look at, because there is no such boundaries possible, so it is difficult to remove the polyps, and especially even identifying the polyps, right? Sometimes the polyps are covered with mucosal fluids, and which creates also problems to detect the polyps. And the most important thing, as I mentioned, that polyps are having camouflage properties. That means it is having high similarities with the surrounding tissues in terms of colors, in terms of the texture. So, and sometimes, and that is these are the main reasons why actually the miss rate is so high. And polyps are often compounded by indistinct boundaries. We have already distinct, and we'll see whether the existing methods could have to address this kind of issues or not, right? And as I mentioned, that yes, there could be a lot of polyps at the same time in a single frame, right? So how to detect all those polyps? Because if one of the polyps is missing, so that polyp, that missed polyp, right, may lead to colorectal cancer. And these are some of the problems of which the doctors used to face while detecting the polyps, right? And that is why we are interested in designing such a robust algorithm which can detect the polyp and provide the precise and boundary information to the clinicians in order to reduce the miss rate. That is what is the major goal here. Yes, there are a few companies who have started working on this, and there's one company. There's something called as one product known as Medtronic GI Genius, right? You can see over here. So this is a flat polyp, right? Very difficult to you can say detect this kind of polyps. Was very if you look at the texture and all, so it looks very similar to the background and all. So that is why it is sometimes very, very difficult to identify the polyps and all. And this particular, you can say, product by the Medtronic GI Genius, right, as a kind of tool, you can say, it's a kind of computer-aided diagnosis system, which we already discussed. It's a kind of tool which can be seamlessly integrated with the endoscopy, or you can say colonoscopy machine, right? and then you can see the result over here, right? So here is the, you can say, the product, or you can say, right, the tool, right, which can be seamlessly integrated with this, so which will help us in detecting all those kind of polyps, right? I have also few videos to show you, but okay, let me check whether it is there or not. This is the product description and all, right? That's what they are claiming, that yes, it is performing well, but still there are some issues, right, that needs to be, you can say, solved or resolved. So I hope my screen is visible. You can see, yes, this kind of polyps, right? It's very, very difficult by the naked eye detect. Right? But with the help of this AI technologies, obviously, computer vision technologies and deep learning technologies, I have also another video. You can see the left side one is without the, actually the GI Genius, right? I mean the without the CAD tool. And the right side one is with the tool. Now you look, now you watch the video. You see how difficult it is to identify the polyps and all, right? Sometimes it is not visible, and this kind of polyp will be easily missed by the clinicians, right? But now if you look at the output produced by the AI based CAD tool, right? So it's really important problem, right? Because the number of cases are increasing rapidly, and of course we need to design, right, such a robust approach which can be used in real time, or if it can be used for real time monitoring of this polyp and all. Fine. Fine. There is some issues over here. Just a minute. Yeah. So let us also look at some of the existing methods, right, on this polyp segmentation. Basically, the problems are here again of multiple types, right? Either you can think of classifying the images into different types of gastrointestinal disease, right? Because or you can say whether it is colorectal cancer or not colorectal cancer, like that. Otherwise, you can, if you want, you can also have a detection problem where there is a polyp. You need to only provide especially the location, or you can say the location where there is a tube or where there is a polyp. And if you want, you can also provide, or you can also solve a segmentation task over here. That is even more powerful, or that is even more important, where you can also provide the boundaries, right, of the polyps, which are very, very important for the doctors for resecting the polyps and all. So segmentation is a very, very important topic for colorectal cancer, where you can segment the polyp regions, right, which are sometimes very difficult to identify, as I mentioned. We've seen a couple of challenges while segmenting the polyps and all, because the polyp itself is having camouflage properties, and the nature of the polyps are always complex, right? So segmentation is one of the tasks, but classification also can be done here, right? Even if you want, you can also detect. So detection is also another task. where you can only provide the bounding box where there are polyps. Segmentation, is also going to give us the boundaries of those polyps those are present is even very important, right? So that is why there are several, you will find there are several research on polyp segmentations in the literature. So again, it all started with this unit architecture and the REST unit plus plus architectures and all. So where you will find the unit and its variants have been initially applied to segment the polyps. But what it is missing is this kind of architectures are having the limited ability to deal with the boundary informations, which are very, very important. So people have tried to come up with some approaches like Planet and all. These are all CNN-based approaches of which can be used to deal with the boundary informations, right? And there are also a couple of approaches people have developed over the years to deal with the diversity, the scale diversity of the polyps. We've also seen the polyps having different shapes or different sizes, right? So people have also tried to introduce these kind of approaches to deal with the scale diversities of various polyps. But overall, if you look at all our convolutional neural network based approaches, and they fall short of capturing the global feature relationships, which is very, very important, right, in case of polyp segmentation. So at the same time, the generalization performance of these approaches are also very, very limited. Then, as we all know that yes, vision transformer based approaches are very, very good at capturing the global contextual information from the image, although it lacks in capturing the local informations because of these properties, especially because it is having nice capability to acquire global feature relationship. So transformer approaches have also been explored in the area of polyp segmentation. And the methods are trans unit, unit R, PVD cascade, CT-net. These are such, the unit R also we've seen, I think in the segmentation lecture, we have seen what is unit R, trans unit kind of architectures we have seen. And there are also different architectures like PVD cascade and CT-net, which are based on transformer, right? So we all know that transformer is good at capturing these global feature relationships, but it also lacks capturing the local informations, which is even more important. Even the generalization performance, if you go through the literature of those approaches, are still limited, right? So what actually people have thought later on, then why not to have such an approach which can capture both local information as well as the global information, right? We'll see. How we have combined both convolutional neural network and transformer together to capture local and global feature relationships simultaneously, right? Another important, very important type of foundation model which is used for semantic segmentation is known as segment anything model. I don't know how many of you have heard about this approach, which is a foundation model and very well known for its excellent generalization performance capabilities, right? So because this SAM has been trained on millions of the images, right? On the natural images especially, right? And then its capability on the on-scene data set is really remarkable, right? So that is why SAM has become very, very popular. So not only SAM, we have also different types of foundation models. And now there is a question here that how can we use these foundation models? These foundation models are very, very large and it cannot be. And then this kind of SAM kind of model has been initially applied on the natural image domain. But what we want to use this foundation model, of course, right? What we know that transfer learning can be one of the options here. Use this foundation model to solve polyp segmentation task. But SAM has not trained on polyp segmentation task or polyp-based data sets. It is trained on natural image data sets. So now you want to use the SAM to solve a polyp segmentation task. And what we know, the transfer learning is the solution. But because the model is very large, even the transfer learning takes a huge amount of time here. So that means the fine tuning of these kind of approaches also takes a huge amount of time and demands high computational overheads. So then what is the solution? What is the solution here? How can we use this kind of approaches? Because this is very, very important for the generalization performance. And this kind of, if we can adapt this kind of models, the generalization performance of the model is going to be really high, and which is really important for solving real-time problems. because ultimate goal of any tool is to perform well on the on-scene data, right? And these kind of approaches are well generalized and can be, if it is possible to adapt this kind of architectures to solve a target task, which is nothing but polyp segmentation in our case, so then our jobs will be the easier one. So how to do this? So of course, as I mentioned, that transfer learning is the solution. But again, I'm saying that fine tuning of the SAM model, which is a large model, right, also takes huge amount of time, and the training time is really, really high. Then how to overcome this kind of situations? We need to use this model, this powerful model. So now there's only one option here. You can opt or you can follow these adapter modules. These adapter modules are the lightweight modules, and we can learn these adapter modules, which will help us, right, adapting the SAM model to the polyp segmentation task, right? So there's a SAM model here. Directly fine-tuning this takes a lot of time, right? And it is not possible if you don't have much amount of data, as well as if you don't have much amount of resources, computational resources. So what we can do here is we can design something called as adapter modules, right? Which can inject the information to this SAM module. Which information? The polyp related. These are the colonoscopy images, let's say. So you can extract the information from the colonoscopy images using the adapter, which are lightweight models, and you can pass the information to the SAM model through these adapter modules. What is our task? Our task is to only fine tune this adapter, and adapters are now connected with the SAM, and the SAM now can be easily get these informations from these adapter modules. Which kind of informations? The domain specific informations, which are nothing but the polyp related information, right? So our goal is only to train this adapter module, not fine tune the SAM module, which takes, right, a longer training time. We'll see how we have addressed all these problems by using or by following adapter modules or by introducing some of the other concepts, right, one by one. So here is actually the glimpse of our recent contributions in the field of polyp segmentations, right? So one is in ICIP 2024, as one of the renowned conference in the field of image processing and computer vision, and WACV, and where there are several architectures like Unit R, Trans Unit kind of architectures, right, have been published. Mikai, where starting from Unit, there are several other architectures you will find Mikai. So we have also got a paper in Mikai 2025, which I recently presented, right? And also we have got an opportunity to present our paper orally, which right, as it's really, I mean, you can say there are only 1,000 papers or 1,076 papers been accepted in this particular conference, and out of them 76 papers have been selected for oral presentation, and out of 76, our paper is one among them, you can say, right, where you could able to present our paper orally. I'll discuss actually all these three approaches one by one. Right, I'll start with this, and then I'll go to this architecture, and then I'll go to this architecture. Right, so there is a link here, right, from here to here, and then from here to here. Right, there's a link, right. So I've started with actually this architecture. And this architecture, if you look at, the first architecture is known as a multi-scale convolutional transformer architecture. So from the literature, what we have observed, right, I already mentioned that, yes, there are approaches on convolutions, a convolutional neural network. There are also approaches on transformer-based, architectures, right? But what we know that, yes, if we can have a single architecture which combines the strength of both convolutional neural network and transformer together, it will be easier, right, to capture the informations, basically the local and global informations together. And the ultimate goal is to, of course, to enrich the feature representations, right? And that's what we did actually here in this particular architecture. If you look at it, is again based on encoder decoder architecture, where in the encoder, what we have introduced is a set of multi-scale feature extraction blocks. Instead of taking only 3x3 convolutions or only convolution or sequential convolutional layers, what we have applied is we have applied different convolutions, right? We can say operations with different filter sizes, and we have not used the vanilla, or you can say the traditional convolution operations. we have used the separable convolution operations, right? Just to reduce the number of parameters. When I say separable, so when I say 3 cross 3 convolution, so by separation, it means that we'll be having two one-dimensional filters. One is 1 cross 3 and one is 3 cross 3. One is along the rows, one is along the column. Right? So if you can represent this 3 cross 3 filter, right, in terms of two one-dimensional filters, and if their outer product, right, if their outer product, let's say this is vertical, this is this. So if their outer product, right, is going to be, right, if the outer product of these two particular vectors is going to be the same as this 3 cross 3 filter, then we can call it as a separable convolution, right? You can just go through the literature to know more about more about the separable convolution and all, and how, where it has been introduced initially and why it is very popular in reducing the number of parameters, right? So here you can see 3 cross 3 if I'm using filter. So like the number of parameters are going to be 9, but in this case, the number of parameters is going to be 6. Secondly, you can reduce the number of parameters, right? And why I've used multiple number of convolutions here? Of course, we want to analyze the polyps at different scales, because we know that polyps are having different sizes as well as shapes, right? So every time you will find in each of these stage in the encoder, you will find there is a multi-scale feature extraction block followed by, a cascaded attention block, which is nothing but a sequence of channel attention followed by a spatial attention. You can see over here, there are 3 blocks, right? And our goal here is to just focus only on the important regions and ignore the unimportant regions. And this particular stage, this particular block has been repeated here. And here is the bottleneck layer. And in the decoder, if you look at here, in the decoder, we are using something called as transformer, or you can say, layer, a transformer layer, which mainly consists of modified self-attention blocks. So what we have seen in the self-attention is this part, right? But here, which basically captures the pairwise partial relationships within the feature map or within the features. We have also included the pairwise channel informations. You can see over here. This is a pairwise channel information. This is a kind of spatial self-attention. This is a kind of channel self-attention. We've just combined them together, and that's why we're calling it as a modified self-attention block, right? And then we have used this kind of attention blocks to make a transformer layer here in the decoder. The decoder, we are not using any, this multi-scale feature extraction block and cascaded blocks. And the decoder only we are using the transformer block here, right? That means the decoder part is full transformer part. And there is also a skip connection like unit. We have also the skip connections where from the corresponding stage, we are actually taking the features and then we are concatenating it. And then we are passing it to the feature structure as well as this modified self-attention and all. So this was actually the idea of, behind this proposed MCT model, and why we have combined this convolution and transformer together, right? And this is the paper name and all. If you want, you can just go through our paper, right? So if you'll be having any queries or any comment, so you can feel free to write to me. I will definitely get back to you, right? So here is just the details of the blocks which I have just now discussed, right? And here is also the details of the modified self-attention block which we have just now discussed. For experiments of validating the proposed MCT net, we have considered actually 3 different types of data set. One is CVC clinic, one is Capsar seg, and one is CVC colon DB. And here is just the implementation setup and the details, how we have splitted the images into training, testing, and validation, and so many other things, right? And here is the quantitative results which we have obtained, and we have compared our approach, right, MCT net, with the architectures, whatever we have discussed, right? You can say that with state-of-the-art segmentation approaches, we discussed UNet, we discussed SegNet. I think we have not discussed DeepLab, but we have discussed a closed architecture, which is known as PSPNet. We have also discussed Rush Unit, Attention Unit, Rush Unit plus Unit R, I think, right? So in the segmentation session, we have discussed all these architectures, and we have just compared our approach with all these state-of-the-art architectures. You can see over here the kind of results which we have got in terms of DICE and IOU is really interesting, right? And it is, of course, superior compared to the other approaches. And you can see the other quantitative results on a data set known as Capsier seg. Here also the same situation, right? You can look at this, the MDI score and the MIO score obtained by our approach, which is superior than the other approaches. And here is the result on another data set, CVC colon DB. But what is most important to observe here, our model is outperforming other models, that is fine quantitatively. But let us also see some of the qualitative results of why is our model performing well and how it tries to capture the precise boundaries of the polyps. So now we look at here. So we have considered actually two examples from three data sets which we discussed. You can see over here. So that this first column contains actually the original images. The last column contains the ground truth images. And this is actually the results obtained by the MCT-net. So now you can consider any case. You can consider, let's say, the last case, a sample from the CVC clinic DB dataset. You can see the ground truth. You can first look at the input image, then look at the ground truth provided by the clinicians, and then look at the output of our approach, and then you compare with the output of the other approach. Right. So our model is almost accurate, you can say. What I can say here is the boundaries are precise, right? And if you look at the output of the other approaches, the boundaries are not that precise, right? So you can also see another cases where there are two different polyps, and sometimes it is even difficult for certain methods to detect all the polyps. Sometimes there are a lot of false positives you can see. So these are like lot false positives, right? False positives. So there are a lot of false positives you can find over here in case of other approaches. But if you look at the output produced by the MCT-net architecture is something like this, something close to the ground truth approach. So which basically tells us the effectiveness of the proposed approach, and it is providing better results only due to the combinations of both the convolutional neural network and the transformer, where you can capture both the local information and global information together. That is one of the reasons. And here is just some of the results of the ablation studies which we performed just to uh, check the importance of each of the individual components like MFE, and there's something called as a CAV here, and there is MSAB, right? So we've already seen all these things, right? I mean, in case of this modified self-attention block, so there are two types of attention. If you remember, one is positional and one is channel based, right? So earlier we've seen that the positional self-attention mechanism, and here it is actually channel based self-attention mechanism, right? And here you can, I mean, what I'm trying to show here is like when we consider all the components, including the multi-scale feature extraction block, the cascade attention block, as well as the decoder part especially, right? This modified self-attention block, when we are combining all these four components together only, we are getting better performance, right? Although this MCT-net is performing well compared to the existing state-of-the-art approaches, what we have observed when this kind of approach is applied to the unseen datasets, right? So the performance is degraded. So then we thought of adapting the SAM architecture, which is really good at generalization performance, right? Or which is well known for its excellent generalization performance on the unseen data. But as we know that directly using SAM or directly using or fine tuning the SAM to solve a medical imaging task is not that easy. It's not a straightforward one, right? Because of the lack of domain specific knowledge, as well as, right, the high requirement of the computational resources. So what we can do is we can adapt the SAM architecture, although there are few issues with the SAM architecture which we have seen just now. But now there is one question that how to use then SAM, right, with you can say in the presence of less amount of data, and how to also reduce the training time, right? So then, as I mentioned, that we develop something called as adapter-based fine-tuning strategies, right, which will be helping us to fine-tune the SAM, which takes a lot of time in general, right? So to fine-tune the whole SAM model, and of course, SAM is having uh, generalization capability. I mean, better generalization capability, and that is also one of the major reason why we want to use this segment anything model, right? And this is actually the paper from where actually we got inspired that yes, adapter-based fine-tuning is really important. But here they have just done adapter-based fine-tuning to fine-tune the vision transformer models, right? So not the SAM model, but we have use the same concept of using or introducing the adapter modules to, you can say, fine tune the SAM model. So how exactly, I mean, how this SAM architecture looks like, what its majorly contains is nothing but a SAM encoder, there's a SAM decoder, there's a prompt encoder, right? And the SAM encoder is not nothing but a WIT, you can say, WIT architecture only. So yeah, so this is another contributions which we submitted to WSEV, and that has been accepted in WSEV 2025, right? So if you look at the title of the paper, it is like Mamba guided SAM architecture for generalized zero shot polyp segmentation over here, right? So what is Mamba and all? I don't know how many of you heard about this Mamba and all. But what is our goal, as I already mentioned, that yes, we wanted to use or adapt the SAM architectures to solve polyp segmentation task. And then we observed several limitations of directly adapting the SAM model to the polyp segmentation. And then we thought of introducing adapter-based fine-tuning to fine-tune the SAM model. You can see over here, this is actually the whole architecture or the whole framework for the SAM Mamba. So as you can see here, so there is a SAM encoder here, and there is a SAM decoder, and there is something called as a prompt encoder here, right? But this prompt encoder always demands a set of prompts, right? And we'll see how we have also addressed those problems, right? SAM encoder is nothing but a hit-based architecture, right? And you can see now here it is. So SAM encoder is freezed. But what we are training here is nothing but the adapter modules. So these are like the adapter modules. This is an adapter module. This is an adapter module, and these adapter modules are nothing but actually the sequential, or you can say the sequence of two cross attention mechanisms, which takes inputs from the SAM and gives information to the SAM as well, right? So this is how actually the adapter model looks like here. You can see over here. It is taking input from the vision transformer block, which is there inside this SAM encoder, and also takes information from the previous layer, like this. So now you look at particularly this figure, right? So this the input image is also passed through the beat blocks, which is already freeze. That is the SAM encoder block, and then again we are passing the original image to the Mamba prior module here. And what is this Mamba prior module? Again, it is a kind of adapter only, adapter module, but it is directly applied on the input images, and which initially extract the features at different scales and then try to find out the global relationship, right? Using, or you can say the long range relationship using the Mamba blocks. Here you can see Mambas are nothing but state space models, are very good at capturing long range dependencies in sequence, right? And the time complexity, I mean, the computational time required by this Mamba is actually linear. But in case of self attention, which can also be used to extract the long range dependencies, is a quadratic one. But in case of Mamba, it is a linear one, and that is why it has become very, very popular nowadays, right? And also we've used the same thing over here. After applying Mamba over here, we are getting a different set of features, and then we are combining all those features here, and then we are passing these informations, especially the polyp related informations, right, to the adapter modules, and then the adapter module pass the information to the beat block, also takes the informations from the beat block, right? And then this process is continued, right? For each of the beat block, you will find one adapter modules, and all these adapter modules are trainable, right? Hit blocks are not trainable, it is fixed, or they are freezed, right? So one more contribution also we have here. What is that contribution? One contribution is to follow this adapter-based fine-tuning and also introduce this Mamba-based prior to send some prior information to the V8 block, prior polyp-related information, right? And another thing, as I mentioned, that yes, SAM is having also decoder block, which consists of something called as prompt encoder, which always demands prompt. So during inference time, it is difficult to actually find out the prompts, right? So then what we developed, or you can say what we have done to address this particular issue is we have made the training strategy different. That means the training strategy is of two types here, or you can say there are two stages in the training process. So one stage is to first. So here, the one stage is nothing but to first generate the pseudo mask from which you can generate the prompts. So the prompts could be anything. The prompts could be like the bounding box, so it could be anything, right? So bounding box is one of the prompt which is usually given during the decoding process. But as I mentioned that yes, whenever we will validate our model during the inference time, we won't have something called as this bounding box or these prompts. So that is why we have generated the mask first from the encoder. Of course, there'll be some upsampling layers and all. So we can generate a pseudo mask which can be used as a prompt encoder, right? And then because it is prompt dependent, so we're trying to make it independent. So we are generating the mask here. From there you can generate the prompt, and that can be sent to the SAM decoder, right? So this is the training stage 1. So in training stage 2, what we can do here is we can fine tune all the layers like the SAM decoder and all the adapter and the Mamba prior model. You can see over here. So these are trainable, but rest others are like freezed. So that's why I've said that the training actually involves here two different stages. One is for generating the mask, and the second one is to train the whole SAM model. That means train the SAM decoder as well as the adapter and Mamba prior modules. And here is the details of actually the blocks, whatever we have discussed right now. All these blocks, right, including this Mamba prior block, which is like this only, where we have initially applied multi-scale spatial decomposition to decompose the images at a different scales from fine to coarse level, right? So with the help of convolution layers with different filters like 3 cross 3, 5 cross 5, 7 cross 7 and all. And then we are actually applying the global average pooling and global maximum pooling over the concatenated feature. And then we're trying to find out the relationship between those features and all using one-dimensional Mamba here. And here are the details of, you can say, whatever I've discussed, all the components, the details of all the components of the proposed Mamba prior module, and how the training stage is different. You can see over here what kind of objective function or loss function we have used. It's a combination of dice loss and binary cross entropy loss. And the training stage, as I mentioned, right, it is a two-stage training process, where in the first stage, your task is to have the loss between the ground truth as well as the output from the, or you can say, the encoder, right? And the second stage, what I've explained is that we need to also fine tune the decoder as well as the encoder part. I mean, especially in the encoder, we are only looking at the adapters, not the WIT blocks or not the SAM blocks, right? So to validate this approach, because the SAM is very good at performing, right, on the one scene data, right? So we have used here 5 different data sets to verify the effectiveness of the proposed SAM Mamba model. So these data sets, like the clinic, CVC clinic DB and CAPSAIR, are used for training the model, right? So the set of images from CVC clinic DB and a set of images from CAPSAIR segmentation have been taken together to train the model. And then we have tested on the rest of the images on these 2 data sets. And these 3 data sets, like CVC clone of DB, ETs, and CVC 300 are only used to evaluate the performance of the model. That means these, the data sets, you can say the samples from these three data sets have not been, used by the proposed model during the training. The model has trained on the combinations of the samples taken from CVC Clinic, DV, and CAPSAIR. And now we need to check that how it is performing on the on-scene data, which is captured from different demographic regions and using different imaging devices. That is what actually we have done. And here are some of the common things whatever we have done. And we have some we have used, or you can say implemented this approach on NVIDIA Tesla A100 GPU and all. Here is the quantitative results comparison with the state-of-the-art approaches on the scene dataset. So when I say scene means, those are like CAPSAIR and Clinic DB, right? So I've already shown you CAPSAIR and Clinic DB, right? And you can see the results. The red color text here represents the best results, and the blue color text here represents the second best results. Now you can see in most cases our model, right, would able to achieve better performance compared to the state-of-the-art approaches and state-of-the-art convolutional neural network as well as transformer-based approaches. You can see over here the dice value is this much, and in this case the IO value is this much. And in this case, the dice value on the Clinic DB dataset, the dice value is 94.2, and the IOE value is 88.7, right? So there are also few approaches which achieves even better MOAU than the proposed approach. So here is again the quantitative results on the on-scene dataset. The model has not seen any of the samples from these two datasets. And these are the results whichever we have obtained. You can see from here, right? The SAM member could able to, right, outperform the other state-of-the-art approaches and achieve an AMDI score of 92 and an AMDI score of 85.3 compared to the other approaches. Right? So this basically demonstrates the generalization capability or the strong generalization capability of the model, right? Because the results on the on-scene data is quite interesting. And that is why actually we were interested in adapting the SAM model, right? Because we know that SAM models are very good at, right, performing well on the on-scene data sets, which is nothing but the generalization performance. There's also one more data set on which we have tested or we have validated our approach, which is SAM Mamba. You can see the results over here. The results are really high compared to the other state-of-the-art approaches. You can see in terms of die score, in terms of MAE, that's the error, right? So it should be minimum, right? So that's why we've used down arrow over here. So this value has to be minimum, and rest of the other value has to be maximum. So you can see the maximum value is obtained by our approach only. So I'll show you also a couple of qualitative results where you can further verify the effectiveness of the proposed SAM model. Here are some of the qualitative results of which we have obtained using SAM Mamba, and we have also compared these results with other approaches, other state-of-the-art approaches, starting with UNIT, UNIT++. There's a PRANET, which is one of the, you can say, state-of-the-art architectures, a very popular state-of-the-art architecture in polyp segmentation. And you can now see this is an original image. This is the ground truth. Now you see how difficult it is sometimes for the clinicians to identify the polyps, right? And then this is the result by our approach. And this is the result. These and others, you can see that you will always find a lot of false positives, right? A lot of false positives in this case. But if you look at the results of our approach, it is quite closer to the ground truth image. So similarly, in case of the second image here, you can see it is difficult to identify the polyps. There are two polyps here. These are the ground truth provided by the clinicians. Our model could able to identify and provide precise boundaries of these two polyps. But if you look at the results of the others, sometimes there are a lot of false positives, and sometimes it could not able to, like PRANET and CityNet could not able to identify the other polyp, right? Here it is very, very difficult to identify the polyps, right? These are the results on the seen datasets. And now we'll see the results on the on-seen dataset. So here are the qualitative results on the on-seen dataset. Now you can see first two belongs to one dataset, second two belong to one dataset, and this final two belongs to another dataset. So what basically we're trying to show here is that how is our model performing well on the on-scene dataset in the real time. You can say if somebody will give us any image, so our task is to identify the polyps accurately. So whether our model is also predicting the polyps and its boundaries accurately or not. So you can see the cases here, right? In this case, there's a plot polyp, and there are many approaches which leads to lot of you can say false positives, including UNET, SFA, and there is something called as PRANET here, right? So this one is a PRANET. Fine. Now you can also look at this scenario, right? In this scenario, if you look at this scenario particularly, so it is very difficult actually. This kind of scenario is very, very difficult, right? Because the boundaries are not distinct properly. So our model could able to give the results close to the ground truth, but still there is an issue here. Could not able to give the proper boundary information, right? And if you look at this particular situation, it is very, very difficult to identify, right, the polyps. But there are actually two polyps present in the, present in this image. That's what the ground truth says here, provided by the clinicians. And if you look at the results of our approach and the other approaches, so the UNET could not able to identify the SFA net here, could not able to identify the polyps. It only gives lot of false positives. Sometimes only one, sometimes it is two, but both of them are combined. But our approach could able to give only the informations here, yes, that there are two polyps, but the boundaries are still not clear. That means this kind of approach, whatever we've discussed, right, is still failing, right, or fails to give better results in case where the polyps are having weak boundaries, right? So here there are polyps with weak boundaries. So in that case, so this model fails, right? So then how to tackle these kind of problems, right? So that is what is our next contribution, where we have introduced something called as a boundary distillation modules, which will take care of these boundary parts, which will try to distinguish the region, the polyp regions and the non-polyp regions, right? Here are some of the results on the ablation studies. Yeah, few approaches. If you are choosing adapter, and then in the Mamba prior block, we have used multi-scale decomposition. If you remember, that's MSD, and there's a Mamba block. So here you can see, whenever you are including this MSD block and Mamba block, there is an increase in the parameter value, but still there are also increase, right? There's also an increase in the, I can say, quantitative values in terms of dyes or IOE value. You can see over here. And here D1, D2, D3, D4, D5 are like the 5 different datasets which we discussed on the seen dataset as well as on the on-seen datasets. This is another ablation study on this MSD block only, where we have used multiple, you can say, convolution operations, right? So what is the need of this? So you can also see whenever we are choosing multi-scale information along with the Mamba blocks, it is really performing well compared to the other different configurations we have. And here is the learning progression you can see of that particular approach, that is SAM Mamba. So you can see here is an image. So this is a learning progression in the training approach, or you can say, sorry, in the encoding process. And what we have got is this kind of region, right? Polyp regions from the encoder part. But in the decoder, we are trying to refine it, and what kind of result we are getting is something very close to the ground truth, you can see. Right? Okay, so I'll take just a 5 minutes of break, right? And then I will start discussing on the final contributions, followed by some of the challenges and future scope, and then I'll show the demonstrations. So will it be okay, sir, if I take 5 minutes of break or 4 minutes of break? Amit, sir? Fine. So am I audible? Is my screen visible?
Yes, sir. Now it is visible.
Okay, okay. Thank you. Yeah. So what we have seen we have seen actually two different approaches which we have proposed, but one approach is the combination of convolutional neural network and transformer, where you could able to address the issue of combination, address the issue of what I can say is address the issue of combining both local and or you can say the global informations from the images. And in the second approach, although it was performing well on the scene data sets, it was not performing well on the on-scene data sets. So that is why we propose something called the SIAM Mamba, where we have used adapter modules or adapter-based fine-tuning to train the SIAM model right? And then because training the SAM model is always takes a lot of time and all. So then, and then in that also in that architecture, we've introduced something called as a Mamba prior module to inject, you can say, polyp related relevant informations to the adapter and of course into the SAM, SAM encoder modules and all. Fine. So that is what actually we have seen. But only one thing, whatever we have observed from the SAM encoder, that although SAM was performing well on the on-scene data set, but there are few cases where the polyp boundaries are weak, right? Where the boundaries are indistinct, that the SAM model could not able to detect those polyps, or could not able to segment properly those polyps having weak boundaries. So then we thought of how to then we thought of introducing something called as a Mamba guided boundary prior module. I will discuss in detail what is exactly that. So that, I mean, from the limitations whatever we have observed from the previous approach, right? So we thought of introducing or infusing the polyp relevant boundary informations to the SAM, right? To further achieve the robustness in the SAM prediction. And the goal is to actually deal with the weak boundary polyps. I've shown you few cases where the boundaries are weak, and I want to identify, let's say, the polyps in those cases, right? And that will definitely help us, right, in identifying different types of polyps, whether it is weak boundaries, whether there are distinct boundaries and all. So in all cases, it is going to be work well. And till date, there will be no, there is actually no such specialized technique been developed to deal with this weak boundary polyp segmentation. And that is what actually we have done here, right? So we have just introduced an approach here. That is, of course, a SAM-based approach to deal with this weak boundary polyp segmentation problem. So then, how did we handle the problem of weak boundary polyp segmentation? So just by introducing something called as a Mamba-based, you can say a Mamba guided boundary prior module. I'll show you what exactly it is. Right. This was the overview of the architecture which we proposed, right? And you can see over here, there's a SAM encoder. There is, of course, a decoder here. We discussed all these parts earlier in the previous approach. And this is actually the main contribution here. Right? So in place of the standard, you can say, adapters and all, so we are, I mean, including along with this adapter, so we have also something called as a boundary distillation module, you can see over here. And there is one more improvement here. So instead of only using the 1D Mamba prior block, so here we have introduced something called as a 1D 2D Mamba prior block. And this 1D 2D Mamba prior block will help in capturing the global informations in different dimensions, like in channel dimensions and at the spatial dimension. And that is why actually we have used both one-dimensional Mamba and two-dimensional Mamba over the images to get the more important semantic informations from the polyps, which is sometimes even may not sufficient, because right, the kind of output which you are getting after the SAM encoder may not contain also the boundary information. That is what we have seen even after introducing this 1D 2D Mamba, which is good at extraction of the global informations along different dimensions like channel and spatial. But there are also some issues with the boundaries. That means the kind of information which we are extracting from this encoder, right, may not contain the boundary related informations. And then we thought of introducing something called as a boundary distillation component over here. What we are trying to do here is we are considering the polyp mask, right? The mask of the polyp. We are also considering the mask of the non-polyp regions. And then we are performing a cross attention between these two. Then this cross attention is going to help us in finding out the relationship between the polyp and the non-polyp regions. As I mentioned, we need to first understand the relationship between the polyp and the non-polyp regions, right? So that means we're trying to distinguish between the polyp and the non-polyp regions. And then whatever the output we are getting over here, we are distilling the knowledge to the feature map, or you can to the embeddings of the SAM. So this is actually the SAM embedding. You can see over here. right? And now we are trying to introduce, or you can say, we are trying to distill the boundary related information into the sham embeddings, right? So then what we are trying to do here is, then we are fine tuning the SAM model, especially here the SAM decoder and all the adapter modules, including the boundary distillation component over here. Because this boundary distillation component takes the mask of both polyp and non-polyp, but during the inference time, we won't be having the mask of both polyp and non-polyp regions. So this is the only part of training. So this is only used for the training. So this is not going to be part of the testing, right? That is what it is mentioned over here, that BDC, that is a boundary distillation component, is only used during training to refine the SAM, right? And of course, to to refine the SAM means to, of course, to refine the feature learning ability of the SAM, right? So this is not the part of the testing only, right? So during testing, you will only use other path, and you are not going to you are going to ignore this path, because this demands the mask of both polyp and the non-polyp regions, and that is why we have now excluded this particular component during the inference time. Right? And this work, whatever we have discussed, has been accepted in MICAI, right, 2025. Fine. And the architecture, if you look at, I have already shown you what is 1D Mamba prior module in SAM Mamba. So we have made a little bit contribution over here, right? So that means, earlier it was only one-dimensional Mamba, which could able to capture only the channel interactions globally, right, within the feature map. But here we have also used a two-dimensional Mamba, right? And this two-dimensional Mamba here is facilitating to capture the global dependencies, right, along the spatial dimension, which is very, very important with linear time complexity, right? So this both one-dimensional Mamba and two-dimensional Mamba all together helping us in extraction of, right, you can say, enriched global informations along the channel dimension and the spatial dimensions, right? And that is what that is what is the major contribution here is this block we have introduced to a two-dimensional Mamba. So we can see that is how actually you can build the one-dimensional and two-dimensional Mamba block, which is really important, right, to capture the long-range dependencies of the sequences and all. Like in the previous case, here also we are generating the pseudo mask first, and then we are sending those pseudo mask as a prompt encoder to the SAM decoder, right? So our model is not prompt dependent, right? We are generating the pseudo mask, that means the prompt, and then we are using that prompt to the SAM decoder, because this is not going to be, right, with us in the inference time. There will be no such prompt available. And yes, again, the same set of data sets we have chosen, right? There are two scene data sets, as I discussed, and there are three on-scene data sets, and these three data sets are only used to check the generalization performance of the model. So now you can see the results, right, of different approaches compared to our approach, right? So this is these are the quantitative results of our approach. Here, the green color denotes, you can say, the best results, and the blue color text represents the second best results. You can see over here, in most of the cases, our model is achieving superior performance in terms of DICE, MIOU, and then further also metrics which we have considered, including this MAE. This is MAE, right? You can see over here. So we have compared with SAM Mamba, right, which is our approach, and there are several other CNN-based approaches. These are like CNN-based approaches. Here are some. Here is one transformer-based architecture, and this is one Mamba-based architecture, right? So our model is really performing well, right, compared to Mamba-based, transformer-based, as well as convolutional neural network-based approaches. You can see on the scene datasets. On the on-scene datasets, you can see the results are also prominent. You can see there's a improvement in the results, right? On the on-scene datasets itself, you can see there's an improvement in the results. So what is most important is, like as I mentioned, that whether our model could able to solve the weak boundary issues or not. That is what. So to see the impact of our approach on those kind of cases, so we have chosen such cases where our model is really performing well, not generating so many false positives compared to the other approaches. So this is the qualitative results on both seen and unseen datasets. You can see. So these are 3 on-scene datasets, and these are 2 scene datasets. These are 3 on-scene datasets. Right? So on the scene datasets, of course, it is performing well compared to the other approaches. Right? You can see this is the input image, and here it is very, very difficult to identify the polyps. There is a polyp over here. We can look at the ground truth. Right? Here is a polyp. Right? That means here is a polyp, which is very flat and sometimes missed by the clinicians, right? So these are by the different experts, and then I mean these ground truths are taken from different experts, and it is like in the mutual decision of several experts and all. Fine. And now, if you see the results of our approach and the results of other approaches like Siam Mamba, we have seen, yes, it could able to identify there is a polyp, but there's a boundary issue here because the boundaries are weak here, right? So in this case, if you look at it, the boundaries are not precise, but this is right close to the ground truth. And you can also see the case which I've already shown you, right? In case of each data set. Now you look at this particular case, and this is the result of the Siam Mamba, where although it could able to identify there are polyps, UNet could not able to identify, UNet plus plus could not able to identify whether there are polyps or not, right? Even in case of SFA, there are a lot of false positives, you can say. In case of PRANET, which is also state-of-the-art model, it could not able to detect the second polyp over here, which may lead to colorectal cancer, right? In case of MegaNet, so both are considered as a single polyp, although they are different polyps. In case of Sam Mamba, although it tells there are 2 polyps, but the size, right, it could not able to identify the precise boundaries. But now you see the results of our approach. That is only because of the introduction of this boundary distillation component as well as the 1D, 2D Mamba block, which really helps in distinguishing which of the pixels or which of the tissues are like polyp and which of the tissues are non-polyp and all. You can see. You can also see a lot of other cases we have, right? If you go through our paper, also we have provided a lot of other results in the supplementary file, right? You can go through our supplementary file and check the results of right different cases of seen and unseen. Fine. So here are some of the results of the ablation studies which we have performed. I mean, that basically tells the importance of each of the modules which we have proposed, right? And coming to the conclusion and the future scope part here. So what we've seen, yes, out of the 3 contributions we have made, that Sam Magiev, that's the last approach which we discussed, is really performing well compared to the others. It is also addressing the long-standing challenge of these weak boundary polyp segmentation, right? And we have seen also it outperforms the CNN-based approaches, Mamba-based approaches, BIT-based approaches, and all. At the same time, it also demonstrates excellent adaptability to the on-scene datasets. That means we have seen right an improved generalization performance on the on-scene dataset. But there are also a couple of limitations which we have observed, right, in this particular architectures. Like we have plus 3 million parameters. If that means the SAM Magiev is having right 3 million more parameters than the SAM Mamba model, right? And there's also slight increase in the G flops. So SAM Mamba actually is having 423 G flops, which is really, really high. And this again SAM Magiev, right, is having 431 G flops, which is really high. And these also this may create problems while deploying this kind of architectures in a resource constrained environment. So then in the future, what we can do is we can think of you can say distilling, or you can say transforming the knowledge of the large foundational models like this to small baseline models like UNet plus plus, right? So that the deployment can be easier, right? The deployment can be easier in the real world scenarios, basically what I'm talking about, right? Yes. So here is actually my team, like my former 2 of my former interns, Tapas Datta and Snehasis Machi, and one PG student, Niladri and all, right? So we have also released the code actually for all these approaches, right? So if you want, you can contact us And here is also the link for the last approach, right? We have not yet released actually the code for this, which has recently been accepted to Mikai and all. So, but we will release it very soon. If you really need this kind of code, then you can just send us a request email. So then we will send the code, or we will share the code with you, right? I must also thank the Anusandhan National Research Foundation, who has supported, right, to develop all these kind of things, right? And of course, my institute also, MNIT Jaipur, right? I think there are a few other things which I could not able to discuss yesterday because of the time constraint. So I think still remember there are few challenges and which we discussed yesterday in case of medical imaging, right? Where I could not able to discuss these many points, right? Especially heterogeneity, generalizability, and all, right? So now if we see all these points, it will look really interesting to us, right? This heterogeneity, that means what we have seen in most cases, whenever we develop some algorithms, we compare with the state of the art algorithms, and then it is fine. We are performing, it's our model is performing well on this kind of data set, and it is, and then the major problem is when we validate our approach on the on-scene data set. So most of the time, the performance drops. So why it is so happening, we have seen also today, right? And then what is the solution here? It is because of the heterogeneity, right? Because of the collection of the images from different imaging devices, collection of the images from different demographic regions. But we need to deal with these kind of situations, right? Because we need to design such kind of computer-aided diagnostic tools that should work on any colonoscopy images or any kind of medical images that may be collected from different regions using different devices. Doesn't matter, but it should work on the on-scene datasets as well, right? So how to actually deal with these kind of issues, and that is also somewhat related to the generalizability. That means the generalization capability of the model. You can explore also some of the domain adaptation techniques. Transfer learning could help you to some extent, right? Because transfer learning means the model is already trained on a large data set, so you are just transferring the knowledge of that particular architecture to solve a task at hand. But generalizability, again, just to achieve better generalizability, you can also again think of using or adapting the foundation models like SAM, which we discussed, is very popular for generalization performance and all, for its excellent generalization performance on the on-scene data sets. So today we have seen what is the SAM, right? And SAM is a foundation model, or you can say the semantic segmentation. And although we know that yes, adapting SAM is not that easy to medical domain, we have also seen the tricks to be followed or the strategies to be followed to use or to adapt SAM to the medical imaging domain, right? There's a lack of transparency and interpretability. What it basically tells us that why is the model performing well, why is the model not performing well? So how to explain? This will actually, this factor is going to increase the trust factor of our model, right? Otherwise, doctors and the clinicians are not going to accept our concept, are not going to even appreciate us or appreciate our AI-based technologies. So if they ask us that why is your model performing well, what is the reason behind the improvement in the performance? So we need to also talk about the explainability at that time, right? We can provide, there are a lot of different approaches we can provide over here. Like people are talking about something called as GradCam. There are a lot of, you can say, variants of, you can say this class activation maps we have, like GradCam++, ScoreCam, and there are different types of, you can say, right, you can say heat maps, or you can say visualization results, which may help us in understanding whether my model is focusing on the important parts or not, whether my model is ignoring all unimportant regions or not, right? That is what is very important here in this case. In case of medical imaging, it is very important. Difficulty in capturing global contextual information. So of course, I mean, we have seen how to deal with this kind of issues. CNN actually, CNN models struggle to capture global contextual informations because of the limited receptive field. But this vision transformer kind of models, right, can be helpful in capturing this global context. But what is more important is, can we have local and global together? That means we're talking about CNN and VIT together, which is known as convolutional vision transformer or convolutional transformer. We have also seen today one model which combines both CNN and VIT together, and how to address these issues or how to capture both local and global information. Fine. And also there are different types of attention mechanisms, and because in VIT, VIT could able to achieve this global information only because of the self attention mechanism it is having. And we have also discussed about the self attention mechanism. So there are also alternatives to the self attention mechanisms, like Mamba is one of the alternative. This large kernel attention is also an alternative to the self attention, which can be explored to extract the global information from the medical images. So multimodal data is also playing a very, very important role nowadays, right? So instead of using one particular type of data or one particular type of medical imaging modality, so if you can integrate, or if you can take different type of medical imaging modalities, so the decision making capability of the model is really going to be high. So that means what I'm trying to say here is, let's say instead of taking only one, let's say for example, fundus imaging, right? So instead of taking the fundus image of a patient and to send it to the model to take the decision, what we can do, we can also have the OCT of the same person. We can also have angiography of the same person, and we will send all these informations to the model, right? So there are different types of multi-modal based models that have been proposed in the literature, right? You can pass different modalities to different models, and then you can combine the results, or you can also pass the different modality informations to the model. Model will fuse the informations from different modalities and then can take the decision, right? Because there are also some important, because all the you can say medical imaging modalities are having some pros and cons, and maybe the OCT contains some important information that fundus doesn't contain. The fundus contains some important information that OCT doesn't contain, right? So that is why multimodal, you can say multimodal, designing multimodal based card system is really very, very important. At the same time, people are also now talking about something called as visual language models, right? Visual language models, right? So it is very, very important. Visual language models where you will not be only focusing on the visual features, that means from the images. You may also have some important informations, right, in the form of the text, right? It could be a report, it could be anything, right? And how to just combine the visual features as well as the text-based features, right? Using the approaches like you might have heard about something called as clip, that's also made clip and all, right? So you can just go through and you can check how this language is also helping, right, the vision models to improve the performance of the model. So these are like, the current trends in the field of medical imaging. So it can be applied to any field of the medical imaging, whether it is polyp detection, whether it is, fundus image analysis for the detection of glaucoma, diabetic retinopathy and all. So you can also think of designing something called as a multimodal data-based model or visual language-based model to solve the problem, right? Fine. So now I'll show you some of the demonstrations on attention mechanisms as well as segmentation algorithms, right? I think yesterday we have seen some demonstrations on classification using the convolutional neural network, right? Which you can design from the scratch, and you can just train the convolutional neural network. That is what we have seen, and also we have seen how to use transfer learning concept, right, to solve a problem, right, or how to use a pre-trained model, right, to solve a problem using this transfer learning concept. That is what we have seen. Today we will see actually two different things, right? One is like attention mechanism, implementation of attention mechanism. I'm only going to showcase one particular type of attention mechanisms, which basically consist of two different types of attention. One is channel attention and one is facial attention. And both of them are applied sequentially, one after another, right? So this is actually the attention mechanisms, the whole attention mechanism, and we can call it as a global attention block. And this global attention block consists of channel attention first, followed by self attention, right? We'll see how we can implement this. And this is actually one block, I can say, plug and play module or plug and play block, which can be integrated with any architecture or any convolutional neural network architecture, right? If you want, you can also include this kind of mechanism after each block of the convolutional neural network, like after residual block, after dense block and all. But including this attention block after each of the block or each of the layers may introduce large number of parameters. So sometimes people used to also include, or you can say integrate, this kind of attention mechanisms after the last convolutional layer. So what you can do is you'll be having some images. You will pass it to a CNN architecture, let's say pre-trained CNN architecture. For example, let's say ResNet. And then you can apply this global attention block over here. I mean, you may get some output of the feature map having size S cross W cross C. You can apply this GAV over this to further refine this feature vector. And the kind of feature you will get, feature map you will get is S cross W cross C, which can be passed to the global average pooling block, or you can also flatten the features, and then you can pass it to the dense layer, or you can say fully connected layer with C nodes, where C is equal to the total number of classes, right? If you are solving a 3-class classification problem, so this FC layer or dense layer is going to have 3 number of nodes, right? Followed by a softmax activation function for solving a classification problem here, right? So now we'll see how to actually, implement these attention mechanisms, especially this global attention mechanism. And this channel attention mechanism we have seen, squeeze and excitation in case of self attention, spatial attention also we have seen, right? There is something called as, you have to first find out the global average, or you can say, we can also find out you can also apply global average pooling or global max pooling across the channel dimension, right? And in this case, what you remember is still the channel weights are 1D. I mean the weights, that is G of X if you remember, and this is 2D. That means the size of the weights, channel weights will be H into W into 1, and in this case it is 1 cross 1 cross C. Because in case of channel, you are actually looking at C number of weights that will be multiplied with this H cross W cross C. And in this case, you want to only focus on the important positions, and we have H into W number of positions. You'll be having this many number of weights that will be element wise multiplied, right, with the input here. And then what you will get is nothing but a spatial wise attention map, right? So let us look at the code, how we can implement it. Only the syntax is going to be different. As I mentioned earlier, we need to first mount with the Google Drive, because that is where actually we have saved our data set, and then we have to import the necessary libraries, whatever is required for our problem statement. Then in this particular data sets, we have 2 folders already, one for training, one for testing. There's no folder for validation. If you want, you can just again split the train set into train and validation. And then here are some of the, right, you can say the codes to, if you want to display an image, how it looks like, what is the size of the image and all, that is what also you can see, right? So it is not required, but if you want, you can just, if you want to see the image, so you can also load any image from the data set, and you can also display the image. And if you want, you can also print the size of the image and all. And then the same steps, whatever I've shown you yesterday, that we can follow. Then like data augmentation and all applied on the training set. And now this is the main code here. You can see this part is the model, right? And this part is the attention block, right? So first what we have done, we have loaded a DenseNet model here. And of course, we are considering the ImageNet weights here. That means the pre-trained DenseNet block, right? With the input size 224, 224 cross 3. And then we are removing the top layers. And then we are inserting the global attention block. That is what we are trying to do here, right? Whatever I have discussed. So this is like a DenseNet here. So instead of ResNet, I can take DenseNet 1 to 1, right? And here is the output of the last convolutional layer. And then we are applying something called as, that means the output of this last convolutional layer can be known as out1, right? So this is a tensor H cross W cross C, and now this out1 will be passed to the global attention block. Then what is this global attention block? It is nothing but a sequence of channel attention and a spatial attention block. You can see over here. So these number of codes, these lines of the code are for the channel attention, and these lines of the code are for the spatial attention. So let us see what are the lines we have inside this channel attention. As I mentioned, in case of channel attention, first we need to perform either global average pooling or global max pooling, followed by 1 cross 1 convolution. If you remember, 1 cross 1 convolution, it's like squeeze and excitation, right? For the first convolution, I've taken ReLU as an activation function. For the second, it should be sigmoid to have the weight values in between 0 to 1, if you remember. And then once this X is actually now the weights, and now this X and inputs, that's the input here, H cross W cross C, is going to be multiplied element wise, right? And then whatever you will get is CA. What is CA here in this case? CA is nothing but the output after this channel attention, right? And the output after this channel attention CA will now be passed to SA, that is the spatial attention. You can see the CA is now the input for the spatial attention. And okay, there's a, okay, if you want, you can include a convolutional layer here to make it learnable, right? To make it learnable, you can use a convolutional layer, either kernel size 1 cross 1 or 3 cross 3, whatever, it's up to you. And then you can perform the sigmoid activation function over it to have the values between 0 to 1. And next, you know that you have to multiply that H cross W cross 1, right? You can multiply this H cross W cross 1 with this value. Now you see, with this means the output of this CA. You can see here now, this in this case, this X is nothing but the weights, which is in terms of H cross W cross 1 is now element wise multiplied with the CA, right? CA is nothing but the output after the channel attention. And then what we are finally getting is nothing but this the results of this spatial attention, right? And this is what you are getting here at out1. If you are applying global attention block over it, and you are getting the output over here. That's the enriched feature. You can see the attention feature map we have. And after that, as I mentioned, we can apply a global average pooling, right? Or you can flatten the 3D tensor into a one-dimensional like this. Either you can use a global average pooling or you can use a flatten. But flatten is again going to give us more number of filters, right? Global average filtering also is widely being used, right? And at the end, you will be having a dense layer. That is what we have discussed. Dense layer having 3 number of neurons, which is equal to the number of classes, followed by a softmax activation, which will give us the probability value. You can see there is a probability, there's a softmax activation, and the number of classes means here it is the class names. That means you need to identify how many distinct class names we have in the data set. And then the length, that means this basically tells us the number of, or you can say, the nodes we should have in the output layer. Fine. See, and then everything else is same. So it is like transport learning only. Earlier we were not having only this block. And if you want to insert this block after each of the convolutional block or each of the convolutional layer, then you can also do that, right? So you can integrate this kind of block with any block or after any block in the convolutional neural network, right? And here are some of the results we have got, but I have not run actually the model for sufficient number of epochs and all, but rest others are going to be same only. Now let us go to the next part is like how to implement unit, right? Using TensorFlow, and I have also code for PyTorch, right? So this is actually the main architecture of unit, if you remember, right? So unit looks like this. So this is an input image. This is actually the output mask, and here is unit basically. The convolution block followed by max pooling. This is like max pooling. These are convolutional block 3 cross 3, 3 cross 3. Again 3 cross 3, 3 cross 3. And then there is a max pooling block. This process is repeated. And then like here, right? This is like 1, 2, 3, 4, fine. And again, you'll be having 4 number of decoder blocks here, right? So in the decoder process, you know that you have to also take the inputs from this side. This is a skip connection. And then you will also take the output from here and you will combine both of them. That means concatenate both of them. And then it will pass through the convolutional layers. The same process. Here there is this process. This is transpose convolution. This is decoder, right? This is encoder. This is decoder. This is X. This is Y. The Y is also a mask here. So we need to provide this X as well as the Y to the model, right? And here you need to also apply a 1 cross 1 convolution with C plus 1 number of layers, right? So that is what we want to implement, right? So how to implement then this architecture especially? Now you can see, right? So using TensorFlow and Keras, I've imported the layers and the other things. You see how the in unit, right, can be implemented easily. In the encoder part, as I mentioned, it consists of 4 stages. At every stage, we'll be having 2 convolutional layers followed by a max pooling layer. You can see here. C1 is now going to the input, right? Sorry, P1, I'm sorry. P1 is going to the input to the next stage. And then you'll be having 2 sequential convolutional layers having 3 cross 3 filter. ReLU is the activation function. Then you will apply max pooling. Then again, the same process is repeated over 4 times. That means it will be having 4 stages like this. Stage 1, stage 2, stage 3, stage 4. There will be some bottleneck layers at the end. And then finally in the decoder, as I mentioned, in the decoder, first you will apply this transpose convolution. And then you will take the input from the corresponding encoder layer, you will concatenate them, and then you will pass it to the sequential convolutional layer. That is what is happening here. You can see, right? First, we have applied a transpose convolution, right? So here the kernel size is 2 cross 2, stride is 2, means we want to double the size of the input, right? And then we have concatenated the results of U6 to C4, right? So this is basically C4. And this is basically U6. So these two has to be concatenated. Similarly, this is going to be U7. This is going to be concatenated with U3. You can see over here. U7 and C3 is going to be concatenated, right? And this always this followed by after concatenation, you'll be having again 2 more layers. You can see over here. After concatenation, you'll be having 2 more convolutional layers. This process is again going to repeat it for the 4 times. And finally, you will be having one 1 cross 1 convolution at the end. That is what we know. If the number of class is only 1, so you can also use sigmoid activation function over here. If the number of classes are more than 1, you can go for softmax activation here, right? So we have also discussed for every pixel, actually, you will get a lot of probability values. It all depends upon the number of classes you are having, and then you can solve the problem, right? And this is how actually we have just now built an UNet model, right? Now people may ask you that how can you implement, let's say, RES UNet model? What is RES UNet model? Just if you introduce a residual connection at each stage, like this. This is a residual connection. Oh, sorry. This is a residual connection over here. So this is a residual connection over here, right? So what changes you have to make in the code then? What you can do here is, so you can just write after this. So what you've got is P1. Now this P1 has to be added with this input, right? So that is what you can do. So that will become, right, the REST unit architecture. So if you want to, let's say, pass this output of this first stage into a attention block, so you can also do that. You can just introduce attention block here. And you'll pass P1 as the input to the attention block. And let's say you are again getting P1 or A1, whatever is the output. And in this attention block, you can use any kind of attention, whether it is channel attention, spatial attention, and all. So accordingly, people have actually made the contributions, right? So it is not that difficult, right? Because functions are already there, and only your task is to, include, or you can say integrate some of the additional components into the corresponding architecture. You should at least, if you know, if you have knowledge on functions, if you have knowledge on like arrays and all, so then you can easily implement any architecture related to UNet or any other architectures, right? Also, I have the implementations using PyTorch, right? If you want, I can share with you. So it is again not that difficult, as I mentioned, that everything is same. You can see everything is same only. Only the way we have written the code is something very different. So here, what we are trying to define is a convolutional block. So inside the convolutional block, we are mentioning everything that there will be 2 convolutional block, right? That means we are trying to, we are trying to actually first define something called as each stage here, right? So you can see over here. So there's an encoder block, which basically consists of this convolution, 2 convolutions, and 1 max pooling. 2 convolution and 1 max pooling. Similarly, in decoder, we need to first concatenate the input from that side. First, we need to also apply convolutional. See, you can see convolutional transpose convolution. The output will be concatenated with the previous output from the encoder. Then you can concatenate it, and then you can perform convolution, 2 convolution operations. And this process this is the whole encoder decoder block. And now you can see the whole code. There are 4 encoder blocks, there's 4 decoder blocks, and there is a bottleneck layer, right? Again, in the final layer, you will be having right, a 1 convolution with C+1 number of what I can say is filters, right? And then you have to design the whole implementation setup, and you need to also provide or initialize the hyperparameters carefully, and then you can train the model, and you can test the model, right? So while training, you need to pass both the image as well as the mask, right? So here are some of the results which I've obtained using only UNet. You can see this is the original image. This is the ground truth. So where all these retinal vessels that are present in this image are segmented. And this is the output of the normal UNet architecture, which we have just now seen. There's no residual connection. There is no dense connection. There is no attention mechanism, nothing. But only UNet is trying to give us this kind of result. You can see but there are few more branches which is still missing over here. You can see there are a lot of branches which are still missing in this. Right. See here are some of the other results. It's not that difficult to implement all these algorithms, right? So it is very easy to implement all the architectures, whatever we have discussed, right? So I'll stop here. I'll share actually all those things with you, right? I think if you are having any queries, you can write them in the chat box. I'll be happy to take few queries.
Okay. Ah. Thank you, sir, for joining with us. Dear participants, so now we have ended our 11 days, or I should say 12 days long journey. We have started with the 24th or 22nd September, and now at the 4th October, we have completed total our 11 days online FDP. So thank you for joining, because possibly means you all have attended all the sessions very means patiently, and I know that being a means listener, it is a very hard job, especially for online platform. Okay, so thank you for joining with us. Now, means we have a just informal validatory function where we seek some input from the participants. Okay, so if anyone would like to speak something, then we can unmute yourself and we can allow you to speak, because you have heard from us from last 11 days. Now it is time that we can hear from you. Apart from that, just quick update that tomorrow there will be a quiz. So please be sure that you attend that particular quiz. And yes, am I audible? Thank you, Gita. You want to say something? Yes, anyone wanted to speak something? If Ankita, you want to say something, because you are typing something, so that's why I thought that if you want to speak something. Just those who want to speak something, then we can unmute you, no problem. Yes, anyone? No one. Okay, so it seems that everybody is now fed up with the 11-day FTP. Okay, and now possibly you wanted to have some rest. Okay, so again, I thank you all of you for joining this particular online FTP Smart Healthcare Technology Opportunity and Challenges. Regarding the certificate will be provided to you possibly within a week. Okay, because there are some background work has to be completed, like attendance verification and as well as the quiz, whatever is being provided. So that also you need to attend. Okay. So after that, we will issue the certificate through mail. Okay. So don't worry that you will get a certificate within a week. Okay. So means if not, then you can just ping me. There is no problem. Okay. So one question: how many batches are completed? Narendra, I'm not getting your question. One question: how many batches are completed? I'm not getting. Narendra, can you elaborate your question? Thank you, Siddharthan. Thank you, Pooja. Thank you, Ankita, for providing your nice feedback. I mean, so far it's our first batch. No, 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 Narendra. So this Electronics ICT Academy has conducted so many courses. I don't know exact number, but possibly it is more than 50 in this financial year itself. Okay. So currently also there are two more online FDPs running parallel. Okay. So it's not the first one. Okay. For this particular phase. Even if you talk about overall, like overall, it could be okay for smart healthcare technology. For the smart healthcare technology, this is our second one, and but of course the first is offline, online. Okay, for smart healthcare technology, this is the first one. But definitely, we are planning to have a second one, which is where we want to think about some sort of advanced version. Okay, so, and we are thinking about at least offline. Okay, so that you have some more practice. So that's what we are planning to have. Okay, this time around also we will engage very few person because to be honest that I want to cover the basic of healthcare starting from the very basic. So that's why possibly I have not involved much because possibly 75% of the content is covered from MNIT resource person only. Okay, so because we can be in sync with each other and so that when exactly content is being covered on that particular day because sometimes there is a prerequisite is also there. So that's what which we felt that in a closed group it could be managed better way. Okay. Uh, Maybe we can think about for a hybrid board, but definitely there will be a second session. Okay. There is a question. What is the advantage of Python implementation as discussed by Professor Brad? Deepak sir, are you there?
Yes, sir. Yes, sir.
There is a question. I'm not sure. Means Paswini is asking what is the advantage of Python implementation as discussed by you? And the masks created were already given in the original image.
Yes, yes. I mean, see, PyTorch implementation there are actually different types of implementations, right? So I already discussed, we have different types of tools, whether it is TensorFlow, whether it is PyTorch, doesn't matter, right? So it's up to you which one you want to choose, right? So for now people are preferring PyTorch over TensorFlow, right? So it's up to you. I mean, if you go through both of the tools, then you need to check whether which one is more suitable for you and all, right? And yes, of course, masks you need to consider. Masks are like y only, so you need to provide both x and y to the model, right? It's not like I have provided mask in case of PyTorch and I have not taken mask in case of TensorFlow. It's not like that. You have to consider y along with x, right? Whatever may be the language or whatever may be the tools.
Thank you, Director. And we have uploaded all the video lectures. Okay. In this particular, all the video lectures are being uploaded. Okay, so you can look at whenever you feel comfortable. Okay, the YouTube link is being provided. PPTs are also being uploaded only the Deepak sir. Possibly he will provide me the PPT today. So I will upload those also. So all the materials which we committed that for all the lectures are being provided along with the video lecture. And as I said that this is not the end of our relationship. Definitely, if you have any issue regarding anything, whatever is being covered, you can contact the means speakers. You can contact me also if I can help you out at any point of time. Okay, so that's all from our side. So again, thank you all of you. Thank you for the joining and wishing you a best of luck for all your future endeavor. In the training session, the faculty are free to advise reference books which are useful. Means I think most of the material possibly they have taken it from the online sources only. But if any specific you want a narrator regarding any specific topic, the book, then you do let us know. We can help you out. Okay. Thank you all of you. Thank you. So I am just ending up our session. Okay. Thank you. See you at any other point of time. Thank
Yeah, thank you. Thank you very much, all the participants. All the best for your future. Thank you, sir, Amit sir, for organizing such a nice FDP and for giving me opportunity to share my experience with all the participants. Thank you once again, sir.